Thanks, Jörg. Good afternoon, welcome. Welcome everybody to my inaugural lecture. I will use the next approximately 30 minutes to introduce you to my area of research, that is empirical software engineering, as Jörg mentioned. The students that are here, they already know that slide, so that's my confession. I usually start with that. So I'm a pre-academic, which means that I work both professionally in software development industry and in academia, which is unfortunately not very common, especially in software engineering. Unfortunately, because software engineering is a quite applied domain, discipline. And I can tell you it's different working with industry or in industry, for sure. You learn different things when you actually work in a company and try to do research there. And I want to start with the origins of software engineering because, it's a relatively young discipline, and there are different stories how the term software engineering emerged. We cannot say for sure who used it first, but it was certainly in the 1960s. So Margaret Hamilton is one popular example. She actually led the development of the Apollo space mission guidance computer. She used it basically to say, hey, software engineering is as much engineering as hardware engineering. So that was her usage of the term. And then around the same time, Anthony Oettinger, he was president of the ACM, also used the term in a letter to the members of the ACM. And then we know that end of the 60s, there was already a NATO conference on software engineering. So end of the 60s, the term was already established somehow. And I want to briefly talk about that conference because it kicked off software engineering as a discipline, if you like. And back then, the reason to organize this conference was the so-called software crisis. And projects used to fail because there were hardware issues, because the hardware was not ready, malfunctioning and all that. But now suddenly it was software that was causing issues. That was inefficient, hard to maintain, that often did not meet the requirements, and sometimes was not even delivered, and so the projects failed because of software suddenly. So the call to action there was, hey, we somehow know how to engineer hardware, let's also engineer software. So that was basically the starting point of the field. And then if you look closer into the report that they have published, and it's still available today, the notion of software engineering that they present there is still relevant today. You would call it maybe waterfall way of developing software today, but it's basically the concepts in there still apply. There are many things in that report that still apply today, even things like effort estimation, cost estimation, acceptance testing. All that was in there in the report, but with a very specific view on how software is developed. A few things are actually interesting. So they already distinguished between the actual programming part of software engineering, so writing down the code, and the larger view on software engineering that includes requirements, elicitation, engineering, and also maintenance in the end. And they said software engineering is all that, not just programming. And this is especially important if you look at the discussion around Gen AI today, and a lot of the tooling is actually generating code and test cases, and it's only a tiny proportion of what software engineering is. So software engineering is much more than programming, and that is even apparent back then in that report. And actually this broader notion was also in there that programmers, as they call it, or software engineers, do everything from analysis to maintenance. And you would maybe call part of that today DevOps, even though the term didn't exist. So it's really interesting to look at that report. But at the same time, also a lot has changed. Back then, software was usually business or safety critical. Nobody else could afford to build software systems. It was built for very specific sets of hardware, like the Apollo guidance computer. It was embedded systems in the end that they built. And today you have kids using Scratch to write software actually. You have games, you have all the abstractions in the cloud, serverless computing and all that, all the abstractions you build software on today. And you have tools like GitHub Copilot, which of course were also not around back then. So we have still embedded systems today, similar domains as back then, but much more. The stakeholders are more diverse, the developers are more diverse, the tools are more diverse, and it's just a much broader field today than it was. And since I thought many cannot really grasp how software development worked back then when they thought about software engineering, I want to show a quick video, and I hope that the audio actually works. See? If not, it's also not a problem.
Program 1.
It's just my laptop, but doesn't matter.
On. Bunch, we're all good to go. go. Feet. There you go. Gesture. Off we go. There you go. Release. Let's do another one. All right. That's the listing. It lists it as it reads it into memory. Good credit. Well, that's far as we are very talking now.
And I mean, it was just to make the point, that was software development back then, and they talked about software engineering, and that was the start of the field, but it's completely different to today. I mean, the interface to actually read your code that was, at that point, just read into memory, not even compiled, was a printer. And even if like the compilation failed or the output of the program, it was usually just printed out. And it took like hours to days from writing the code on the punch card. One punch card is just one line of code. And then you had to get time to actually use the computer to run your program. You could have compiler errors, and then you have to go back, basically, writing new punch cards and rerunning your program. And today we have minutes from doing a change and then deploying it to the cloud, and everybody who has basically an internet connection and a browser can use your software. So a lot has happened in between. And my point is mostly that there are still fundamental concepts that apply today that were still already present in the early days of software engineering, but it's just the point that I made earlier. The applications, the tools, the software development is much more complex and diverse than it was ever before. And this leads me to the disciplinary boundaries of software engineering, because also they are much broader than they used to be. I mean, you can have the very traditional view on software engineering. It's this engineering mindset, close to computer and systems engineering. And okay, that's one part of software engineering, maybe the core. But if you don't have a bit of a broader view on software engineering, you cannot answer many questions that software developers in practice face today. And let's just look at some examples. And again, the students know those examples because I used them in the lecture as well. We saw Scratch, visual programming. How can you do that without knowledge about cognition when you develop a visual programming environment? How can you study pair or mob programming, so programming in a group or with an AI assistant, without knowledge about communication, verbal or non-verbal? And also without knowing about the legal situation, copyright, licenses, how can we understand code reuse and also reuse of AI-generated code? So, I mean, you can do that while ignoring all the other disciplines that happen around software engineering, but maybe it doesn't really lead to insights that you can actually use in practice, because software engineering in isolation very rarely happens today. And that's at least my personal experience and observation, that many of the problems that are faced in practice have, of course, their roots in these core software engineering values and practices and processes, but they often have some form of an interdisciplinary component. And we as researchers, if our goal is to impact software development practice, we need to provide actionable recommendations that are based on understanding the actual needs of software practitioners and not the assumed needs. There are enough problems in practice that are unsolved. We don't need to invent new ones and then solve them somehow. And we should also do this systematically, like not just talking to a few people and then thinking you know what practice does. That's exactly where the empirical part comes in. Systematic empirical research to understand the problem space, the problems faced in industry, then of course developing solutions, but then again also evaluating the solutions and their impact. If you see the solutions as a treatment and you see what difference does it make, the new tool I implemented, for example. So empirical methods are also relevant in the solution space. And since interdisciplinary research is sometimes used a bit as a buzzword or without defining it, I can at least provide the definition I'd use. I mean, it's not the perfect definition. I adapted it from a book. And to me, interdisciplinary software engineering research is basically just the integration of concepts, methodology, procedures, epistemology, terminology, data, and some other things from other disciplines into software engineering research. And in the best case, you do that with researchers from the other disciplines that help you doing this transfer, but not always. I mean, sometimes it can also work without people in those disciplines if things are well described enough that you can reuse them. But yeah, oftentimes it makes sense to actually work with people from those other disciplines. And before I conclude this part of the talk, I wanted to mention what I call institutionalized boundaries that also exist between research and practice. Let's look at an hypothetical example that's deliberately a bit exaggerated maybe. So in software engineering, there has been a lot of research on model-driven software engineering. And at the same time, it's something that is only in very few parts of the software industry applied. And I don't want to go into the discussion why that is the case. And the point is that many of those results are published in papers that then tell you, hey, model-driven software engineering improves the quality, and so on and so on. And then from a practitioner's perspective, you could say, yeah, well, I'm not building safety-critical software. Do I really have to do that? I need to quickly respond to customer feedback, implement changes quickly. I don't want to update the models. And for us, round-trip engineering did not really work in whatever past projects. So, and the point is, first of all, it would be great for practitioners to read papers and learn about things that we come up in a software engineering research community, but the assumption that they read papers is maybe a bit optimistic, so we need other forms of communicating findings. But at the same time, also that experience from practice rarely propagates back to research, and then you can work with that and continue. And again, this is why we need empirical research to close that gap. In an ideal world, research informs practice, and you have evidence-based practice, like in medicine, for example. But I think this is not only, it's not a one-way street. Also, practice needs to have a feedback channel to research to actually inform the research on the problems that they find relevant or impactful. So it's not a one-way street, you need both sides. And I think I mentioned it already, but to me it's really important that we as researchers have an understanding of the state of practice, especially in software engineering. Maybe not in all fields, but in software engineering. And to reach that understanding, we need to use empirical research methods. And also learn from other disciplines how they do this kind of research. And finally, to advance evidence-based practice, we also need to invest time in communicating findings back to practitioners beyond papers. And maybe another thing, because a lot of software engineering research is more on problems than on solutions, that's totally fine, but we also need to actually try to solve the problems that we identify, and then again evaluate the solutions that we come up with. And since my field is empirical software engineering, a few words on that. Basically, the first is one of the first books on empirical software engineering, 2008. And back then, they still said that it's rare. Like 10 years before that, it was rare to see claims in papers being supported by empirical evidence. So back then, it was still totally fine to just develop a new tool and argue why this is solving some problem. And today, it's unbelievable, but it's the case. It was the case in the 90s that was software engineering research. No need for empirical backup. Yeah, but I took the quote in 2020. I'm not sure how long it has been a part of the Empirical Software Engineering Journal, but at least today they say that it has become apparent that empirical research is a central component of software engineering research and practice. And actually one of the editors-in-chief of the journal has been working for Microsoft for a long time and is a practitioner himself. So yeah, a lot has changed, fortunately, I would say, in the field. Now I want to show a few examples, and I have a small framework that I use to basically think about the projects I do. It's nothing super complex, it's just a mental model that helps me at least think about the projects I do. So, of course, the things I do research on are always rooted in software engineering, in the stakeholders, processes, tools that I used. They usually also have an empirical component. Empirical studies are part of the projects, and they have this interdisciplinary angle often, not always, but often. And in the central part, it's basically what I outlined, this moving from problem space to solution space and then iterating on that. And beyond this high-level framework are also like themes that guided my research since I started with my PhD. I don't want to go into all the details of that. And it's also not in a chronological order, and it's all somehow also related. It's not mutually exclusive. Things I always cared about is developer experience tool support, so supporting developers in working more efficiently. And this is then always combined, or often combined, with behavioral studies, so understanding how they use tools, for example, also data mining to understand usage patterns and all that. Data-driven decision-making is something that results basically from doing these kinds of studies, and that's what I try to do, at least in the software industry, to work towards that. And another thing I will briefly cover is meta-scientific issues in software engineering. It's also something, if you want to do empirical software engineering, of course, there are also meta-scientific issues. How do we as a community, as a research community, want to do research, and what are our standards? That's more on a more abstract level, but I think it's nevertheless important to advance the field. And behind all the themes are, of course, papers. And from the papers I started as a PhD student, which were mostly about developer experience tool support, to the more recent publications that I did with industry partners, or also actually in industry as a person there with SAP and Grailware, and that's more on the data-driven decision-making side of things. And just maybe in the virtual session there are some of the co-authors, so thanks to all my co-authors. I mean, it's not something I did alone, it's always with co-authors. Thanks to them, and also, of course, thanks to my family and friends, since we're in the thanking mode here, especially my wife, my son, and I selected a picture. It's actually not staged. It's my son when he was 9 months old. He took that from my bookshelf, so he learned about effect sizes already, so he's becoming reviewer too of the future. But with that, back to research. I wanted to just show some selected projects, I mean, of all those that I've shared earlier. One was a study that we conducted very early in the pandemic to understand what this forced work from home means to software developers, and also how the organizations can better support them in now working from home suddenly. And I can't go into the details of the results, but the cool thing about that paper is actually that we had impact beyond software engineering with that. I mean, it was cited in so many different disciplines, ergonomics, psychology, even in the medical domain, management, and all that. And it's just a cool example that we can also have impact beyond software engineering with the empirical work. And it's actually, maybe Paul is in the session. If yes, thanks to Paul for the collaborations. It's actually the most cited paper in empirical software engineering in the journal in the last 5 years. And the second paper, so the one running second, is also co-authored by Paul and me. And I'm personally very proud of that. And maybe if Paul's in there, again, thanks to him as well. And now for the second example, I selected something that's still ongoing. So it was research I started at SAP when I was still working there, and I continue to work with them. And I'm looking forward to also future collaborations in that regard. And it gets a bit more technical, but I try to be understandable to a broad audience. So one thing that you have in software is, of course, test cases. You try to somehow ensure that a certain feature of the software continues to work, that you want to actually detect if something that worked before now suddenly doesn't work anymore. And for that you have these tests that you test your software with, that are automatically executed just to validate whether your software continues working. The problem is that there are cases where nothing changed in your code and suddenly the test fails. And that is what is called flaky tests. That can happen because you use certain anti-patterns maybe in your code, but it can also just happen because of the execution environment. It has nothing to do with your code, and suddenly the test fails. And that's of course a problem, because you cannot really trust your test cases anymore when you don't know, okay, if the test case fails, is there actually a problem? And then people have to start looking into things where there is actually no problem. But you cannot also ignore the failed test case. And that's a problem. It's a huge problem because you can't trust your test suite anymore. And one point I want to make, and sorry for the text here, there are a few bullet points coming in. The thing is that a lot of academic research is about open source projects, small projects, unit tests. And unit tests are small tests that have like seconds maybe of execution time. And on the other hand, you have large-scale industrial systems that have long-running system tests. And this is not just SAP or SAP HANA as a database management system. There are papers published by Google, Facebook that point to the same issues. In large systems, you have larger test cases. And in a database system, you can just think of the database starting, you get data in, then you have certain queries that you execute, and you have expected results. And you just validate, is the result as expected? And since it's a huge system, it takes longer. It's not just seconds. Some of the system tests take hours to execute. It's an exception, but it happens. And it's just a completely different scenario. And then if you have these flaky tests that you cannot really rely on, you have a problem in these huge systems when you now have a change, a new feature, for example, that you want to implement, that you want to get on your main code line, and now suddenly the tests fail. and you don't know, is it actually an issue with the code I just tried to integrate, or is it just a flaky test? And that's, of course, a problem. It slows you down. And a common strategy is to just restart flaky tests. If you know tests are flaky, you just restart them multiple times for the same revision of the code. And if one of the executions passes, then you just accept the change and you consider the others flaky test executions. But of course, this is expensive, especially for these huge test cases. And it's a default strategy that is implemented in pipelines, in solutions all over the place. And yeah, it's just the way it is that companies handle these situations. And there's a second part. You try to prevent these long-running tests to basically block your resources. It can happen that the execution gets stuck of the test case and then it blocks your resource and nothing else can be executed. And for that, developers usually say, okay, I have a test case. It usually runs 30 minutes. If it now runs 50 minutes, I want to cancel and restart it because there's a problem. So these are the two strategies that I used: restarting and then hoping that one of the runs passes, and then having these timeout values to counterbalance the fact that those test cases, the large test cases, might block your resources. And then in the end, one result we had in the study is that almost all runs in the pipelines of SAP HANA are affected by flakiness. And this might sound surprising, but it's just a statistical thing. I mean, this system has hundreds of thousands of tests that are executed, and it's just a matter of statistics that at some point one of the tests fails despite the fact there was no real issue, because many of the failures are caused by the environment, for example, the network being unavailable, things like that, and not actually the test cases. So, but now back to something more visual that maybe everybody can relate to. What we did in this study is basically ignore the developer-defined timeout values. So that's the red dotted line here. And we increased them considerably to see the actual runtime distribution of the test cases, to understand, okay, what's the runtime distribution of a specific test case? And the first thing you see here with the developer-defined values, what can happen is that your test is maybe scheduled on a slower hardware or something like that, and then suddenly you reach this value when usually you don't. And this is of course a problem, because once the timeout value is reached, then you have these restarts that I mentioned, and you have an overhead. Like if you would have waited for 1 more minute and the test then passed, then everything is good, you are relatively fast, and you can continue. But if you just restart the test after the timeout is reached, you have a problem because you have to wait longer, and of course you have load on your system that you wouldn't have otherwise. And it's a trade-off in the end, because you also have on the other end these stall test executions. So the timeout value, we increased it to 30 minutes, you see it there. And this was one example where the test case just blocked the virtual machine for 30 minutes. There was an issue. And if you don't have timeout values and you have these cases, you block the resources for all this time. And that's basically the trade-off. Having too small values leads to restarts that you don't want to have, and having too long values leads to blocking test cases, blocking resources, and it's basically an optimization problem in the end. And what we did there in that research is, first we looked at the data, we identified the root causes for flakiness in SAP HANA, then looked at the most common reasons, and actually the timeouts were one large contributor to that. Then we developed a mitigation strategy to handle this better and evaluated that strategy. And that's basically one of the papers that came out of that, actually published earlier this year, so pretty recently. And I mean, I'm not a huge fan of software patents, but I mean, it's a company in the end, and I was still an employee when we worked on that. So there's also a patent application for a variant of the strategy that we developed there. And then basically, once we got rid of some of the flakiness noise in the data, we were able to go a bit deeper and analyze reasons for flakiness without the noise. And this is also published this year in September, and for that one we even got a Best Paper Award, and this is going deeper on the reasons for flakiness, but it wouldn't have been possible with the other work. And this is basically how we modeled the problem. I won't go into detail, I'm also not a mathematician, but it's really, the notation is really helpful to very specifically define what the problem is that we want to optimize for. And we basically modeled the execution costs and then defined an optimization problem to find the optimal timeout values that reduce overall the flakiness, but also minimize the runtime cost at the same time and balance that. And that's what we did there, developed an approach to optimize this, and then we evaluated it, and actually it turns out that we were able to reduce a lot of the timeout flakiness, like timeout flakiness in the sense that tests are restarted because they run into timeouts. And at the same time, which is a bit counterintuitive, but on average, the new timeout values, the optimized values, are even smaller on average than the previous ones. So yeah, that was a bit counterintuitive, but it makes sense if you think about some test cases having extremely high values that are then maybe set down, and for others we increased the values, and overall it helped to reduce all this noise in the data. And then one very interesting thing is that we also thought, what is our baseline here for the optimization? And we said, okay, the other approach was basically for each test case you look at the runtime and then you derive an optimal value. And we said, okay, the baseline could be, let's just use the same value for all test cases and don't do an optimization per test case. And we also looked for an optimal solution there, and this would be like waiting 120 minutes regardless of the test case. And of course this reduces flakiness even more because yeah, you wait longer, but at the same time the runtime cost is also much higher because in the cases where you block the resources you also have to wait 120 minutes. But then in the end, despite the fact it was our baseline solution, this was actually then implemented because internally this was much easier, of course, to do than doing an optimization per test case. Academically, the other solution is, of course, more interesting, but this was much more practical to implement. And the decision was made that basically reducing timeout flakiness is more important than maybe saving some of the runtime cost. And yeah, that together with this being much easier to implement led to the fact that it was implemented, and you really see it in the data. Like once the static timeout value was rolled out, a lot of the noise got away. And the thing is, I mean, you could say, yeah, well, why has nobody done this before? Why did developers define the values? Well, it's the industry standard. Developers define the timeout values. It's not only SAP, Microsoft, Google, that's the default. They do that. The developer knows best how to define the timeouts. But we used basically data to show that's not optimal. Even if you just use a static value for everything, it's better than letting the developer set the values. And it's also not only about setting the values. If the test suite gets larger, you have to update the value. So it's additional work that developers do that doesn't have any real value. But you cannot just go there and say, like an organization with thousands of people at SAP say, hey, I think I know how to do this better. You need data for that. And we did that, and it was implemented, and you immediately saw the result. And that's what I meant with less flakiness noise. We got rid of a lot of the noise and then could go deeper in actually understanding the root causes. And to summarize this part, I want to basically show this along the framework I've outlined. I mean, the empirical part is exactly this quantitative analysis of the historical data and the simulations we ran using different timeout values. And the contribution to software engineering is then the quantification of the impact of timeouts on flakiness in large-scale software systems and this optimization approach that we developed. And this interdisciplinary part here was actually that we looked at how other disciplines model similar problems, these optimization problems, but also the cost function that we used. And then, yeah, we reused that basically from other disciplines. Okay, now conclusion. I have a few more minutes, and want to conclude my talk now with a few basically takeaways, if you like. You often hear, yeah, well, empirical software engineering, is that really computer science or software engineering? And at least in my view, yes, totally it is. Because empirical software engineering requires you, first of all, to understand how software is developed in industry, in open source, wherever. You need domain knowledge, but you also need knowledge about empirical methods, how to apply them, how to ask the right questions, and also how to answer them then in a way that actually helps people. You need development skills. I mean, you often have to implement, we heard about IDE plugins earlier in an invited talk. You have to implement these interventions to then understand the impact of them. So you actually need to be able to develop software. So it's not only studies. And also, what I find very important is to have an eye on what's happening in the industry, looking at trends, but also to critically reflect on them, not just following the hype, but maybe taking a step back and thinking about stuff that is happening outside of academia. And again, the students know this example, but not all of you in the audience know, so let me repeat that. You might know McKinsey, consulting firm. They, in 2023, said, yes, we can measure software development productivity. We have no idea why the academics have so much trouble doing that. Here's our solution. which basically ignored years of research in software engineering. And as of 2019 already, there was a workshop, a Dutch workshop, and a book afterwards that basically said it's more complex than that. And it's also not only an academic thing. I mean, there's people from Google, Microsoft that attended the workshop that helped drafting that book. And yeah, the consulting firm just wanted to have attention, I guess, and said, no, we can do that. And the problem now is, and that's the takeaway, if you work with companies, especially C-level management, they listen to the consulting firms, and then you come in there and you have to argue why this is not the case or why it's more complex. And that's actually not an easy thing to do. But a skill set you need when you want to work with especially large corporations. And the second point I want to make is that research is used as marketing, or to market software products. And if you look at GitHub Copilot, so one of the popular AI assistants in software development, they say it increases productivity, or they used to say, by whatever, 40%. And if we then look at the studies that they publish about that, what they did is they analyzed usage data of Copilot and surveyed developers, like a questionnaire, an online survey, and combined that data. And you don't have to read this. The important part is the productivity measurement is just a question, I am more productive when using GitHub Copilot, and then a scale to answer how productive you are. So it's self-assessed productivity that they used. But they use it in marketing. So the thing is, if you then look a bit at related work, also with industry partners, so also not completely academic research, we already know that self-rated or self-assessed productivity correlates mainly with non-technical factors. Like the tasks you work on, support you get, and all that. And what does that then mean for the claim that GitHub puts out there? And I'm not saying that these AI assistants don't increase productivity. That's not the point. The point is that it's not as easy as one number that you then use to market your solution. Yeah, then back to our previous topic, research versus practice. So there are, of course, issues of applied software engineering research, especially when you are in industry like I was. It's normal, you have constantly changing business priorities, you have to adapt, you have to be flexible, that's just the way it is. You have to also sell your projects internally, and it's very hard to do that if you need short-term investment with an unclear long-term gain. That's a huge problem to sell these kinds of projects internally. It's not impossible, but just something you have to get used to. And what, of course, is always then asked is a quantification of the potential business impact. Whatever KPI the companies use, that's just something you have to do or not do if you don't like to, but it's something that they will ask for. And this makes foundational research difficult, not impossible, but difficult. It's just something you have to keep in mind. But at the same time, to put it more positively, it's also an opportunity, because if you then work in close collaboration with industry, you can actually go into these topics that they might not dedicate resources to, but maybe somehow find interesting or relevant. That could be maybe promising, but there's no clear business impact yet. That might require you to explore the problem space without an immediate quantifiable impact. Or that maybe might require looking at a lot of research that has been done, like in the AI assistant case, knowing the studies that have been done there. So there is an opportunity in there for academia to go into these gaps that are there, and of course many more. And I want to conclude my talk first of all with basically a summary. If there's one takeaway, then my summary would be there are enough actual problems in software development. Let's use solid empirical research to understand them, to work on solutions, and maybe not invent new problems that are maybe not faced actually in industry. And with that, I want to conclude the talk and say that I want to continue doing exactly this here in Bayreuth. And thanks again for welcoming me. And with that, we can have a few questions. Thank you.